Hello, in this video you'll learn about KMAC hash specifically. Now, if you are already familiar, which you might be if you're watching this video, with HMAC, this is essentially the same idea. You create a sort of a signature for your data, whatever it might be. It might be for some file, for some kind of a data that user sends to another user that you want to completely hide and verify. This isn't obviously encryption, but you want to verify the integrity of the data. And of course, the most common use case might be hashing those passwords, which has been talked about endlessly over many years now. And most platforms implement something, but this is a newer way, a more modern way, and a more better way to kind of approach that. There are a few reasons for it. There is the quantum resistance, so it's sort of more difficult to break through it all. Then there's extension vulnerabilities, so we can't we can more easily prevent those blocks from the attacks and things of that nature. However, in this video we only mostly focus on the sort of practical part of this whole arrangement rather than theory. If you want to read about theory, you should go and read it. I will just say that in all these arrangements there are some nuances. Maybe something is better for this or the other thing, but this new arrangement is actually somewhat faster, quicker, more efficient than the HMAC. But again, do look up that specifically if you are actually interested in performance and things of that nature. You will need to sort of see if that is specifically useful for your use case. That is how it works with all these arrangements. And obviously, whether it's whether you're doing crypto or blockchain or just hashing passwords or doing some file integrity checks or things of that nature, whatever you're using it for, you do need to probably take a look at some of the perhaps documentation or basically charts and tables about this stuff. But to use it in C#, it's a relatively straightforward arrangement. This is C#.NET 9 specifically. That is something important to note because you might not be able to access it in other arrangements. It's running on Windows. It is quite portable, so you should be able to use it in most cases, especially some like web applications, APIs and things of that nature. Should be no problem at all. But just to start with it, there is a very useful feature right here. We have a little comment here, platform support check, and that is exactly what it is. We are checking if this particular platform on which it's running does support this KMAC 128. So KMAC, of course, if you are familiar with HMAC, it's kind of similar, and it's almost exactly the same. It's a bit different, but the idea in the end is exactly the same. You provide the key, you provide the data, and you get your hash. That's it. That's all you need to have. So we do check that and we throw exception or we handle it in whatever way we need, and then we generate the key. Now, the key in this case is 32. I would suggest using that. Again, if you want to use different arrangements for whatever reason, you should look up specifically the documentation, see what works, see what doesn't work, especially if you are generating the key in a more dynamic way, in a more customized way. You do need to check specifically that documentation to see if all your sort of permutations will be accepted. That is quite important to note. The next thing, of course, we just create some data. This isn't really part of the arrangement. Basically, we just need a byte array. So whatever byte array you have, that's what you're gonna use to hash. So again, it could be some data from a file, it could be a password. Most probably common use case at some point will become, this is still a new thing, and most platforms probably won't switch from an HMAC to this right away, as it is quite a difficult task to do that. But this is just how we get the data. So in this case, we get it from string UTF-8, get bytes, we get the byte array. Whatever byte array you have, it doesn't matter. The key is a bit more of a different thing. It kind of matters, the structure and all those things, but obviously the data that you're actually hashing, it doesn't matter at all. Now, we can also use, unlike the simple HMAC, we can have the actual source for the hash, and then we can have a bit of customization, so sort of additional data going into the whole actual thing. This is somewhat useful in some cases. In some cases it might just be ignored, so you might just have a static value, but this can be useful to make it even more safer, essentially. So we can differentiate those MECs with essentially the same key, but for sort of different use cases. But again, whether you use it or not, kind of take a look and see if it's worth it and how it needs to be specifically. It is important to note on all of these things, for basic stuff like password, you hash your key with message. That's probably fine. If you have some more complex arrangement, if you're working perhaps with some blockchain transaction arrangement, doing something of that nature, you do need to get into this a bit deeper, see what are the nuances of this thing, not just that it's a bit more safer than HMAC, not just that it's perhaps some performance improvements and all those things, but just exactly how it works, what it can take, what it can't take, and all those different arrangements. But basically, we have our key, we have our message, and then we have the output length. So that's going to be the hash length. And then we can actually get that hash. Well, for now, we just get the original MAC. So this will be that sort of constructed data, or computed data in this case, not just constructed, for that initial arrangement for the data, which we probably generally wouldn't use, right? There is no real reason for it. Basically, we need to probably just do the hashing of the data in the more straightforward way now. So we get the original one, and then we get the verified. So in general, when you do this, you use hash data, so you create a hash. Now, in this case, just to sort of get back a bit, we create the hash. So this MAC, we could rename it to hash, might be a bit more straightforward, but basically this is your hash. So then we print out the original, or the one we created, and then we can run the same thing again. Now, the construction here is a bit different, so we kind of make it more straightforward, readable, so you can access the source code and find everything you need in that place, and you can see where key and source is. But basically this one is exactly the same method, so it runs exactly the same way, and it should, given that key, message, customization, length is the same exact data as it was in the original MEC, then they should match. And we also have this very useful tool. See right here, we have from the byte, we have sequence equal. This is from specifically from the byte array. It's not from the any of the KMAC arrangements, but it is from byte array. We have sequence equal, so we can compare the byte sequence to the MAC. Now, if you do convert it to base 64 like this, right here, you can compare just base64, and usually you'll probably store it in a database if it is a password as probably as base64 string, although you might have a var binary type in SQL Server, whatever database you use, so you might have different arrangements, but you can actually in C# compare just the byte array. So if it matches, it matches. If it doesn't, it doesn't. That means the integrity has fallen apart, something doesn't add up, that signature essentially is not valid for the data provided. That's it. So if you download a file with a signature that doesn't work, well, there's something wrong. Someone has tampered with the file. And the final piece of this whole example is exactly that. So we have essentially the same message. So all the same records. So we have key, then tampered will be the tampered message, again 32, and customization. So the only difference is this tampered message, and the only thing that changes, we add this exclamation point as a byte to this byte array at the end, and that ruins the whole thing. It doesn't match anymore. Now, it will still create a hash, right? Whatever data you provide, it will still create a hash. But the point of it is, it will not match with the original. That means it will be invalid, and that means someone provided wrong data, someone is trying to tamper with the data, and then you need to prevent access and do all those things. So this is essentially how it all works in this arrangement. Now, if we quickly run it, just to see some of these results, relatively straightforward example, really. We have original MAC right here, the one, basically our hash that we created with KMAC 1 to 8 algorithm, we might call it. Again, the output and the input is really quite similar to HMEC. It's just more of what it is behind the scenes. Although the structure in the code is kind of different. We don't use compute hash and all those things that we do with HMEC, some of these cryptography libraries in C#.NET. And then in this case we also have a valid one, which is exactly the same as the original one. And then the other one, we have the tampered one. So as you can see, we are using exactly the same thing, so exactly the same data for the original one. So that would be the original one, the first one, and this one is completely different. So even in base64 configuration or conversion rather, it is completely different, and of course it doesn't match as a byte array, so it is false. Now, I would recommend, of course, using this if you can use it in .NET 9. This is available. This is safest, more secure, as it is known, than the HMEC arrangements. It is also somewhat faster in some arrangements. So you might also consider that for those use cases as well. But do not rush and change your arrangements if you have passwords for users. There is most likely not a lot of need to make that change just yet. And with that said, we will conclude this video.